Hello student, welcome to chemistry class with Emila. This class is brought to you by Igotha Virtual Learning. And in this class today we are going to be looking at the molecular geometry. And we're also going to look at electron geometry. These two work vis-a-vis, and of course they are important in helping us understand the shapes of compounds and what brought about the shapes and so on. Now let's look at quickly. We look at molecular shapes in previous when it comes to chemical combination or electronic notations. We have the shell and then we have the Lewis structures or Lewis notation. What Lewis notation and structures help us to do is to help us to understand the valence electron in a molecule. Anytime you see a Lewis structure or Lewis notation, it helps us to know the valence electron in a particular molecule. However, Lewis structures are two-dimensional. They are two-dimensional, and then of course molecules are three-dimensional objects. Lewis structures are two-dimensional, while molecules are three-dimensional objects. Therefore, there is need for us to have a 3D structure in order to understand molecules very well. So, molecular geometry, therefore, is the three-dimensional arrangement of a molecule's atom in space. Molecular geometry is a three-dimensional arrangement of a molecule's atoms in space. And some of these arrangements could give us a geometry like this. We could have a molecular geometry like linear, bent, trigonal planar, tetrahedral, trigonal bipyramidal, diagonal pyramidal, trigonal bipyramidal, and octahedral. Okay, so let's look at molecular shapes generally. Geometry and shape of molecules are very critical, and of course we can easily predict the 3D structure of a molecule by simply adding up bond atoms, the atoms that are joined together, and then the lone pairs of electron they are carrying, the atoms that are joined together and the lone pairs of electron that they are carrying. So by this we can determine the molecular shape of a particular molecule or compound. The polarity of each bond along with the geometry of the molecule determines molecular polarity or even the uneven distribution of molecular charge. So molecular polarity strongly influences the forces that are between molecules in liquids and solids respectively. Now what determines the shape of a molecule? What determines the shape of a molecule? Atoms and lone pairs take up space and prefer to be as far from each other as possible. So shape can be predicted from simple geometry. What makes geometry is the combination of and the atoms of a particular molecule and the lone pairs present. But this geometry, from simple geometry of a particular molecule, you can determine the shape. I hope you are getting it. We get it better. Now let's look at an important theory that helps in explaining or helps us in determining molecular geometry. It is called the VSEPR theory. The VSEPR theory stands for valence shell electron pair repulsion theory. The VSEPR theory states that repulsion between the sets of valence level electrons surrounding an atom causes this atom to be oriented as far apart as possible. Now let's break it down a bit. In a layman's language, what VSEPR theory is saying that the best arrangement of a given number of things is the one that minimizes the repulsion among them. That means that if you have atoms or if you have things. Now, when we come to when we talk about things, now we are talking about both atoms and the electrons. So when you have them in a particular molecule, the theory is helping us to understand that we want to minimize the repulsion as much as possible. So therefore, the arrangement we must do must be such that those things, which is atoms and lone pair, are arranged in such a way that there is minimal repulsion among them. It's as simple as that. So if I have atom A and B having whether a lone pair of electron or two lone pairs of electron, or whatever electrons they have, they must be arranged in such a way that it minimizes repulsion among them. It minimizes, so that is what the VSEPR theory is talking about. So what's the implication of this? Let's look at the things we are talking about. In here, the things we talk about is the central atom having about four things. It is having one, three atoms surrounding it with a lone pair. It has boron atom. Here now you have a boron atom surrounding it and a lone pair. So these are the things. Though the atoms and the lone pair are the things we were talking about in the previous slide. Okay, so um, looking at geometries now. These are the geometries that you can see for the these are the geometries you can see around a central atom, and then we could have about five of them or more. When you have when the total number of lone pair when the total number of lone pair or and atoms, when everything equals to 2, when combination of lone pair and atom is equal to 2, you are going to have an arrangement like this, and the geometry will be linear, and then you are going to have a border angle of 180 degrees. When it's 3, you have a trigonal planar at 120 degrees. Please take note of the arrangement and of course the bond angles and the geometry. When number of things is 4, now don't forget we have talked about things here. Things include atoms plus lone pair. So when the things are 2, you have a linear geometry. You have, this is how the arrangement will be, and you have your bond angle like this. When it is 4, you have tetrahedral. You have the arrangement like this, and then 109.5. When it is 5, you have trigonal uh, pyramidal, and of course trigonal bipyramidal. We are still going to talk about that. And then you have trigonal pyramidal to be 120 degrees, and then trigonal bipyramidal you have 90 degrees. It could be 2. There you must when it is octahedral, when the number of things is 6, the arrangement is like this. The geometry is octahedral, and the bond angle is 90. It is important that you learn this well. Okay, let's look at the geometries that we are talking about here. Now, in the Lewis structure, don't forget that our foundation started from Lewis structure. Our Lewis structure give us a 2D representation of molecular arrangement. Okay, but in Lewis now, for ammonia, this is the Lewis structure for ammonia. But when we take it to the electron domain geometry, we are still going to talk about electron domain and electron geometry and molecular geometry. Now, when we talk about the electron geometry now, you have a tetrahedral. That means you have about to the central atom, you have 3 atoms being attached to the central atom plus a lone pair. So all we must do is to count the number of things in this Lewis structure. And then here now, in the Lewis structure, the number of things here is 1, 2, 3, and 4. We have counted it. So there is the number of things that will determine the geometry. The number of things will determine the geometry. In this case, let's look at the electron domain geometry now and the molecular geometry. In electron domain geometry, please follow up. So like I've said, we could have molecular geometry and electron geometry. You have ammonia. This is the Lewis structure. This is the electron domain geometry, and this is the molecular geometry. The geometry is often not please also understand that geometry is often not equivalent to the shape of the molecule. The shape is defined by the positions of only the atoms and not the lone pair. When we are talking about the shape of a molecule, it is determined predominantly by the number and the positions of atoms in that molecule. Whereas when we are talking about the geometry, it is a combination of both the atoms and the lone pair. That's the difference. So in this case now, you have the shape. The shape will be, which is the molecular geometry now. When we consider the atoms, the position of the atoms alone surrounding the central atom, you are going to have the shape to be trigonal pyramidal. Trigonal pyramidal, while the geometry of this ammonia will be tetrahedral, because it's considering both the atoms and um, the lone pair. So, and then again, when you are putting it as electron geometry and molecular geometry, the electron geometry is tetrahedral, while the molecular geometry is trigonal pyramidal. Now, let's furthermore in this our discussion, let's look at geometry versus shape. Geometries versus shape. Within each geometry, it is possible you have more than one shape. In a particular geometry, it is possible you have more than one shape, and of course this is caused as a result of the presence of lone pairs of electron here. Now when you have three atoms, predominantly 3 or 4 atoms, when you have 4 atoms being joined to a central atom, you will have tetrahedral. However, some tetrahedral or arrangement like this could have varieties. You could have more than one shape here. For instance, you can have a tetrahedral geometry and you have a trigonal pyramidal shape. For an example is ammonia that we mentioned the other time. Now, in most cases, this shape now, we said this shape as a result of the orientation or the position of the atom. For the bent, for instance, now look at the bent here. You are the geometry here is bent because it's having two low. Of course, the place of the lone pair of electrons are supposed to be replaced by atom. In in um in methane, in the first one that we see here, the atoms that are surrounding the central atom here are 4. So you have tetrahedral. By the time you get to this to ammonia here, you have 3. That's why we're having trigonal pyramidal. By the time to get to water, the atom surrounding the central atom becomes 2. Now it has shaped to bent. It has changed to bent. So these are um, varying. You will see here that these are varying geometries that you could have. These are varying geometries that you could have. So uh, shape is usually the orientation or the position of only the atom, while geometry has to consider both the atoms and the lone pairs that are on them. Okay, let's look at the linear geometry that has 2 things. Don't forget, we are using thing. In the linear geometry, you have 2 things. An example is carbon, CO2 rather, carbon dioxide. CO2 is having just 2 atoms, which is carbon and oxygen. However, in the geometry, that is how it is being done. You have only 2 atoms here. The geometry is, the arrangement is like this. Now, but you observe an interesting part. On carbon, which is the central atom, there is no lone pair of electron. There is no lone pair of electron. This is the geometry. The geometry here is linear, as it has been arranged. The shape is also linear here. Observe that there is no lone pair of electron. If we are just looking at how the position of the atom, so therefore CO2 will definitely be a linear shape and a linear geometry. Now, when there is in the geometry that has to do with two things, you could only have a possible geometry which is linear. When it has two things, that means the atom is two. If it does not have a lone pair, like you have 2 0 here now, the shape will literally be linear. If there are only two atoms in the molecule should be linear no matter what the geometry is. If there are only two atoms here, take note of that, the molecules will be linear no matter what the geometry is. Now let's take it for that here. Let's take it for that using VSCPR to predict the geometry. For instance, when you write the Lewis structure for it, this is how the Lewis structure is. Carbon is 2 4. It is use 2 electron. Oxygen is having 2 6. So you have one on top, one down, and the one beside. So the one beside combined with one pair of oxygen, also combined with one pair of um, carbon at the left hand side to have 4 electrons, and of course 2 electrons make one bond, so we are going to have a double bond here. The same thing applies to, so this is the Lewis structure of CO2. Now according to the VSCPR, the shear pairs will be as far away from each other as possible. So the distance between electron pair is maximum if the bonds to oxygen are on the opposite side. That's 180 degrees apart. Now what we are trying to say is that the distance between electron pair is maximum if the bonds to oxygen are on the opposite side, because you want to obey the VSCPR rule. They must be far apart so that there will be less repulsion. If oxygen is staying one side, like you have if you, for instance, you bring the second oxygen to where the first oxygen, there will be a great repulsion because they are getting closer to one another. But since they are far apart now, there will be minimal repulsion. That's why they have to be linear in order for us to have a minimal repulsion. So therefore all the three atoms must lie on a straight line. That's why we're having a linear molecule. So it follows on what is called AB2 molecule. AB2 in the sense that A representing carbon, B2 means that we have two oxygen there. You have AB2 molecule. So that's how VSCPR will explain it. Now let's look at a trigonal planar geometry, for instance. When you have three things, that means this is how the geometry will look like. The atoms are 3 and having lone pair of electron. An example is BF3, for instance. On boron is 2 3. That's the valence electron is 3. That means it will use all the 3 electrons to bond with the fluorine. Fluorine is 2 7. So you have 2 2 1. So the one extra will combine with one from bromine to form one BF, and like that, like you have seen in the picture here. So it will use all the 3. So that means that there will be no lone pair of electron on bromine after that combination. So it is having 3 atoms surrounding it with 0 lone pair. Therefore, the shape will be trigonal planar. The shape will be trigonal planar. However, if it is having 2 atoms, don't forget the geometry is still trigonal planar, but we are not talking about shape now. However, if it is having 2 atoms with 1 lone pair of electrons, there will be a distortion here. There will be a distortion. So if it is having 2 atoms with 1 lone pair of electron, there is a distortion in the arrangement. So instead of it being a bent shape, is going to be instead of it being a trigonal planar, it is going to be a bent shape. An example is NO2 that you see there. On NO2, for instance, you have a lone pair of electron on nitrogen. You have a lone pair of electron on nitrogen. So therefore, it's going to be having bent shape. So therefore, there are 2 molecular geometries or shape for when they have three things: trigonal planar if there are no lone pair of electron, bent if there is a lone pair of electron. So when you have three things, this is the arrangement. So when it has three atoms, zero lone pair, the shape is trigonal planar. Two atoms, one lone pair, the shape is bent. And these are the example for the trigonal planar is BF3, Y for bent is NO2, NO2 minus. Okay, let's look at using VSEPR to predict the molecular geometry of boron trichloride. For instance, if you write the Lewis structure, it's important to learn how to write Lewis structure. This is how the structure is. There is no lone pair on bromine. On boron rather. Boron is in group 13 and has 3 valence electron. So chlorine is in group 17, has 7 valence electrons. So the total number available when we combine them together will be 24. That's uh, for total number available. So now there is an exception to boron to octet rule for boron. Boron can only, because it's a metal, can only drop 3 electrons, so it will be left with 2. So that means it is not octet. You want to gain a duplex structure, and it's, of course, will still be stable, because you have said you only get stable when you have 0 duplet or octet configuration. So the 3 BCl bonds stay farthest away by pointing to the corner of an equilateral triangle, giving 120 degrees angles between the bonds. So this is a possible way to ensure that the BCl they stay further apart. This is how we can draw it to make them stay further apart. So therefore, this will give us a trigonal planar geometry, and then BCl3 will be an AB3 molecule. This is how you can use a VSEPR to explain the molecular geometry of BCl3. Okay, let's quickly look at talking about lone pairs and bond angle. Lone pairs are physically larger than atoms. Know that, and then of course their repulsion are greater. So this tend to decrease the bond angle in a molecule. When an atom have lone pairs, for instance, this is what we are saying. For instance, look at um, uh, the bond angles. We are talking about how lone pair affects bond angle. We said lone pairs are larger than the neutral atoms themselves. Okay, then of course, because they have greater repulsion, they will decrease the bond angles of a molecule. If in methane, for instance, carbon do not have a lone pair on it, it's having 109.5. By the time you get to and don't forget these 3 uh, molecules that are here, methane, ammonia, and water, for instance, have a tetrahedral, possible tetrahedral geometry. However, the shape will be different, because methane will be tetrahedral, ammonia will be trigonal planar, and then water will be bent. And then more interestingly now is the impact of the lone pair on the bond angle. The bond angle gets to decrease as you increase the number of lone pair. At 0 lone pair, you have 109.5. At um, one lone pair, you have 107. It has decreased. By the time you have 2 lone pair, you have 104.5 or 105 degrees. So when increase in lone pair decreases the bond angle, it is important you understand this in our study of this geometry. Now let's move on. Let's look at multiple bonds and bond angles. When it has a multiple bond, for instance, you can a particular compound can have a single bond and double bond on it respectively. So when you have a double and triple bond, it places a greater electron density on the sides of the central atom than the single bond. For instance, what we are trying to say is that the sides where you have double bonds, you are going to have a greater electron density than the side you have a single bond, like you have seen. The side with double bonds 124.3 degrees, while the side with single bond 111.4 degrees. Therefore, uh, double and triple bond also affect bond angles. That's what we want to establish here. So it is important you know that. Now let's look at a tetrahedral geometry, for instance, when they have four things. Now the geometry is tetrahedral. When you have four atoms with zero lone pair, you are going to have a tetrahedral shape. An example is CH4. In CH4, carbon have used, because carbon is 2,4, it has used all its electron to bond with the hydrogen atoms. So no lone pair of electrons. So it's going to be tetrahedral. Now, when you move, you still at four things. Now, when it becomes 3-1, that means 3 atoms and 1 lone pair. It becomes a trigonal pyramidal or trigonal planar, as the case may be. An example is ammonia. Then when it has 2 atoms and 2 lone pairs, you are going to have a bent shape. An example is water. And another example of that bent shape is SO2, that's sulfur 4 oxide. So that's how tetrahedral geometry is. Now we can look at trigonal pyramidal when it has, or bipyramidal when it has 5 things. There are 2 distinct positions where we now start to advance under trigonal bipyramidal. Now there are 2 distinct positions that we can have in this geometry. We can have an axial geometry. Of course, this is only applicable to trigonal pyramidal or bipyramidal, as the case may be, or geometry that has 5 things. You can have axial geometry. That means you are looking at it from the axial point of view, like you have seen in the picture here. So at the axial, you are going to have 90 degrees as the bond angle. But when you are looking at the equatorial geometry, from the equatorial point of view, you are going to have 120 degrees. Now let's look at it. For a trigonal bipyramidal geometry, for instance, the things are 5, like we have said. The geometry is trigonal bipyramidal. When we have 5 atoms and 0 lone pair, you are going to have trigonal bipyramidal. An example is PCl5. When you have 4 atoms with 1 lone pair, you are going to have a seesaw. You are going to have a seesaw. Now for that seesaw, an example is SF4. When you have 3 atoms and 2 lone pairs, for instance ClF3, F3, you are going to have a T shape. Then when you have 2 atoms and 3 lone pairs, an example is XeF2, you are going to have a linear shape. So the geometry is still trigonal bipyramidal, but the shapes are different with different examples. So that's how it is. Now for octahedral, when it has 6 things, atoms, when the atom is 6 with 0 lone pair, you are going to have octahedral shape. An example is SF6. But when you have 5 atoms with 1 lone pair, BRF3, you are going to have square pyramidal. And then when you have 4 atoms with 2 lone pairs, you are going to have square planar. An example is XeF4. So please, it is important that you understand these examples, the shape and the geometry respectively. So to give a summary of what we are talking about, when the steric number, that's the number of things now, is 2, you have linear. When it is 3, trigonal, planar, and bent are possible. When it is 4, we can have a tetrahedral, trigonal, planar, and bent. When it's 5, you can have trigonal bipyramidal, you can have seesaw, T-shape, and linear. When it is octahedral, you can have a octahedral, square pyramidal, and square planar shapes. So these are very, very important for us to know. Now to give us a summary again, according to VSCPR again, and their type, you could see linear here, how it is being structured, and the type. very, very important. You have bent here. You have a trigonal planar. You have tetrahedral. You can add more Lewis formula examples to them. You can also have a trigonal pyramidal, or then you have it like this. You have a bent. You have a trigonal bipyramidal. You have a octahedral. So do it to learn all of this. Now, we can also use the VSCPR theory to explain unshared electron pairs. Don't forget that most of the things we have mentioned are based on electrons that are shared, the lone pair that are there, and how they are. So now we look at unshared pairs electron, for instance. The VSCP theory states that lone pairs of electrons occupy space around central atom, just as bonding pairs does. Okay. If you take into account NH3 takes a tetrahedral shape as in a AB4 molecule. The geometry of a molecule refers to the positions of atom molecule. We have established that. So the geometry of an NH3 molecule is that of a pyramid with a triangular base. Just to reiterate what you have said. Then for water you have a bend shape. And then note that unshared electron pairs repel other electrons pair more strongly than bonding pairs does. That is why the bond angles in ammonia and water are somewhat less than 109.5 of a perfectly tetrahedral shape. We have mentioned that many times. Just a recap. Now let's for larger molecules, we have said that the geometry about a particular atom rather than the geometry of a molecule as a whole. In larger molecules, we talk about geometry about a particular atom rather than a whole. For instance, in this large atom, for instance, this is ethanoic acid, CH3COOH. We treat them individually. For instance, the CH3 there is tetrahedral. Normally it's supposed to be CH4. The H has been replaced with COOH. Methane is CH4. The fourth H has been replaced by the functional group COH. That's why it is still tetrahedral, because it has a methane molecule, and then of course being replaced by what's it called by COH. Then the first CO again is 3 because it's having a trigonal planar. Is having from the electron domain. Now you have 2 lone pair and an atom combined together, so it's going to have trigonal planar, which is 120 degrees. And then you have a 2 lone pair again with an hydrogen and a nitrogen molecule. So you are going to have a tetrahedral here, which is 109.5. So what we are trying to say in essence is that for larger molecules, we treat them individually. We treat them individually. We treat each particular atom individually. So you can take more examples to work with. Now, the structure of the whole molecule is only clear when we look at the whole molecule, but the geometry about each atom still follow the same rule. That is what we are talking about from CH3COH. Generally, this is how it is. You have CH3COOH. This is how the molecular structure is, but they follow the same rule. But it becomes clear when we treat them individually. Okay, so let's look at quickly the electron geometry. We have been talking about molecular geometry, and of course we have talked about electron geometry at one point, but to make it more clearer, electron geometry describes the spatial arrangement of a molecule's bond and lone pairs. Electron geometry describes the spatial arrangement of a molecule's bond and lone pairs. VSCPR theory can also be used to calculate electron geometry. The term electron geometry is the name of electron pair or groups or domain on the central atom, whether they are bonding electrons or non-bonding electrons. So electron pairs are electrons that exist in pairs or bonds, as lone pairs as lone pair or as a single unpaired electron. Because electrons are always in motion and their path cannot be precisely defined, the electron arrangement in a molecule is described in terms of an electron density distribution. So why are we saying that? Let's look at the electron geometry of CH4, for instance. How do we calculate the electron geometry of CH4? The molecule central atom is denoted by the letter C. We can see it here. And then the number of valence electron in C is equal to 4 because carbon is 2, 4. So the valence electron is 4. Then the number of electrons donated by hydrogen is also 4 because each hydrogen atom has 1 electron each. So when it is 4, that is 4 times 1, you have 4. That means the total number of electrons within the vicinity of C will be 4 plus 4, which is 8. Why? Because 4 is coming from carbon and 4 is coming from the 4 surrounding hydrogen atoms surrounding that carbon. So you have a total number of electrons to be 8. Then the number of electron groups is 8, which is divided by 2. So when you take the total number of electrons, you divide it by 2, it gives you 4. So the number of single bond present therefore will be equals to 4. The number of single bond present will be equal to 4. Then if you are to count number of lone pairs, that will be the 4. That means once you have divided the 8 by 2, the 4, then the number of single bond to 4, that's 4 minus 4, and that is what? 0. So that means it is having 4 atoms and 0 lone pair. 4 atoms and 0 lone pair. So because it's having 4 atoms and 0 lone pair, the electron geometry therefore will be tetrahedral. The electron geometry will be tetrahedral. That's how to determine the electron geometry of a compound. So you can take other compounds and treat it as well using this method we have mentioned. Okay, so we can predict the number of electron pairs and the electron geometry. When you have number of electron pairs to be 2, the bonding electron is 2 and lone pair is 0. You are going to have linear. For when it is 3 bonding pairs, 0 lone pair, trigonal planar. 2 bonding pair, 1 lone pair, trigonal planar. 4 bonding pair, 0 lone pair, tetrahedral. 3 bonding pair. Now we are talking about electron geometry. Please don't mistake it with molecular geometry or shape. Now when we have a 3 bonding pair and 1 lone pair, tetrahedral. 2 bonding pair, 2 lone pair, tetrahedral. 5 lone pair, 5 bonding pair, 0 lone pair, trigonal bipyramidal. 4 bonding pair, 1 lone pair, trigonal bipyramidal. 3 bonding pair, 2 lone pair, trigonal bipyramidal. 2 bonding pair, 3 lone pair, trigonal bipyramidal. 6 bonding pair, 0 lone pair, octahedral. So we are talking about electron geometry here. Please take note of that. Now, what is a salient difference between electron geometry and molecular geometry? The name of the geometry of the electron pair domains on the central atom. So whether they are bonding electrons or non-bonding electrons, you refer to it as electron geometry. Molecular geometry is a 3-dimensional structure of atoms in a molecule that determines its shape. So it aims in comprehending the entire atom and its arrangement. Additionally, we can look at the difference between them. For instance, you can see that electron geometry refers to the name of geometry of the electron pair, while molecular geometry is the 3-dimensional structure of atoms in a molecule. Electron geometry helps us to understand how different electron groups are arranged in a molecule. Molecular geometry helps us to understand the entire atom and its arrangement. Then electron geometry is determined on the basis of both bonding electron pairs and lone pairs, while molecular geometry is determined by the basis of only bonding electrons, not the number of electrons pairs. So these are salient differences between the two. So we can look at the difference between them. For instance, this is the molecular geometry of water, and this is electron geometry of water. So another one is we could have more from ammonia and the likes. Each of them have their molecular geometry and their electronic geometry. So note that if all of the electron groups are bonded and there are no lone pairs, the electron geometry and molecular geometry are the same. So let's take one of few questions here. Why 2016? The shape of water molecule is what? You can give me the answer. What is the answer, please? The answer is, let's go back, the V shape or bent shape. V shape or bent shape. V shape or bent shape. A supplementary question will be JAM 2019. The molecular shape and bond angle of water respectively are bent and what? 105 degrees. Please take note of that. Bent and 105 degrees, not 109. 109 is for tetrahedral, and but for a bent, the bond angle has reduced because of the amount of a lone pair is, as we have mentioned that. So you have bent 105 degrees and the answer is D. So far we have learned um, about molecular and electron geometry. We have looked at different shapes of molecules, and of course what causes them, and and majorly here we have looked at VSEPR theory. We have a lot of other theories like that, molecular theory, molecular beta theory, and the likes. But for the purpose of this, we have been able to focus on the VSEPR theory and how it explains electron geometry and molecular geometry, and we have been able to look at various geometries of um, molecules. So I hope you have learned a lot. You can do it to take more questions that you can lay your hands on this topic, and then do it to master the tables and of course the uh, the the structures. Of course, you should be able to draw the structures well, predict their geometry, and give relevant examples. Continue to learn chemistry and do it to solve as many questions as possible. Thank you for being part, and bye bye.